All right, for today, I would like to start with two very quick reminders. For your Lab1 Part2, it was just released yesterday. And as you have seen already in the announcement, it's about 2 hours long because I really want to cover all the details possible, find your way to really understand the details, and especially about how you can do debugging of the model. It's really something we're going to do for every single lab, just to make sure you can do it. And also about how you can translate from Pascal into TLA plus predicate. Well, these are the two main things you want to really make sure you grasp. And accordingly, given the length of the tutorial, I thought it might be helpful if we try to extend the deadline for submission of your Lab1. So if you take a look at the course calendar, I just updated it. So you can get until the end of next week to really complete the exercises. The amount of exercises you're supposed to do are just the same. But I think just spend more time on part 2 of the tutorial video. You're definitely going to use them, especially how you can interpret the error trace and other things for a subsequent lab. I think it'll be worth your time. So take your time since you got 1 more week. And to be more precise, if you look at the E-class instruction over there, you can see it's now being changed to February 6th. Okay, just double check. Everybody knows that. Of course, if you can finish earlier, finish earlier. That's not a problem. And then can wait for lab number 2. All right. I just want to draw your attention to some very quick stuff about the highlights. So give you a little bit of guidance about how you're supposed to study for the part 2 of the tutorial very quickly. Okay. Of course, details you will have to take some time to digest. Number 1 is just about how the things are supposed to work in the TLA plus tool. You ought to understand there is one part, the TLA plus predicate, that can be automatically generated. Okay? So this part here, you want to make sure it's in sync with your algorithm. Every time if you make any changes to your Pascal algorithm, you have to make sure you try to retranslate right away. That part can be done automatically for you. And of course, you got to study what's really the correspondence between this algorithm over here and this automatically generated predicate as well. I definitely talk about it in detail in the tutorial. That's one thing. And this part over here also need to be written by you. It will be some Boolean properties that will be checked as invariants or de la freedom. That's what we did. Later on, you can also specify some temporal property once we covered some syntax in the class. And of course, outside the range, you can also put some comments here as well. Right? That big picture is really important for you, especially when you're in the programming test. You want to make sure you really update the right place. And don't really try to mess up this particular place because it can just be generated. Never try to modify it. Okay? Want to pay attention to it. And this part here, don't worry, it's actually built up in the tutorial video in very slow paced. You really want to make sure you understand, let's say given this M0 Pascal program, which we did in part 1. How is that corresponding to the generated predicate over here? Okay, they use something very, very assembly language-like, using program counter and also stack. So I'm sure you guys took 2021 before, right? So maybe, well, you don't need to review anything there. Just remember what a program counter is and what a stack is. That's all you got to do. Right? I also try to explain that in the tutorial video. Just pay attention to them. And then another thing, remember we mentioned before in the introductory lecture, we said in order for you to do model checking, it has to be feasible enough. It cannot be like an infinite system for you to model check. So once you define your algorithm over here, you can instantiate as many models as you like. So you got to watch out for the terminology. In this course, especially in the TLA plus tool, whenever we talk about a particular model, it can be model 1 or model 2. You want to think about what exactly are we restricting. For example, in one case, we might restrict the maximum number of cars in the island and the bridge to be 2. That'll be a smaller system. We can increase it to be 4 and all the way to 10,000 and etc. It can be as many models as you like. That also watch out for that distinction. And this is just some tip, about transferring file. You can just pick it up very quickly. And the idea about an error trace, right? And I want to just quickly mention the connection, which we're going to review today as well. Every time you're trying to verify a system property that's invariance, you're basically saying, for every state in my system, this particular invariant property should satisfy. That's a for all quantification. What a model checker can do for you is to say if the property is somehow violated in a particular state. So it's going to give you the so-called weakness. I'll make it a little bit more precise when we talk about for all quantifier today in the review. So this error trace here is showing you precisely one possible violation. Given this error trace, you are supposed to study that carefully based on the understanding of what's happening over here in the TLA plus predicate, and then work out a solution. So in the tutorial video, I try to be a little bit quick about what the solution should be, but I would suggest you guys try to inject some errors, which I give you some tips about how you can do it. And try to make some error, and then try to look at the error trace over here. Sometimes they can be long, sometimes can be pretty short, but they will give you a very good idea what's really going on, what's going wrong specifically in your model. Right? Just pay attention to it. It's really important. Whenever you're using a model checker, the most valuable thing it can provide to you is an error trace. All right, remember that. And finally, this is this PDF over here summarizes about things you should really put together whenever you're working on the problem. One thing is about state transition diagram, which can be generated by TLA plus tool. I think that this feature is very nice. You can really take a look at the system you just modeled and see if that's really what you want. And then the error trace is just a part of it, subgraph. And then take a look at the error trace, an example here, and take a look at the original algorithm. Put things together and really understand. Yeah, what I just highlighted in 5 minutes, it took about 2 hours to explain. So guys, take time, right? If you really need more time to really digest or any question, let me know. I think it's really important. For subsequent lab, we wouldn't have such long tutorial. I think usually I'll just give you up to 1 hour or sometimes even shorter, just to guide you through some new syntax, and then you will be able to do some exercises. Patrick.
So you mentioned in the first lecture that
yeah.
when we're dealing with automatic model checkers, we have this concern of possible state explosion.
Yes.
When does that actually happen in terms of like picking a bound or like a value for?
Yeah, it's a very good question. Yes. So when can the state explosion really occur? So conceptually speaking, let's say in this case, the larger the value of D, like how we instantiate the model, the more likely it is going to run into state explosion. However, I think for most of the model we're going to look at in the lab, we wouldn't really run into this problem because TLA Plus is claimed to be an industrial strength tool. So I think it's quite efficient to really deal with this. But one sign you can definitely see. Let's say when you hit on the button there on your model checker, if you find that it doesn't really give you any result back, most likely it's running out of memory. Then it's a very good sign of state explosion. Okay, a very quick preview, which we're going to say about when we talk about model checking lecture. What can be the possible result from the model checker like a TLA plus? Let's say you want to check some invariant property. Either you can say, yes, the invariant is true for every possible state, number one. Number two, the invariant is false, and it will give you a counter trace. Don't forget this and possibility outcome number three. It simply wouldn't give you any answer because it's so busy checking the state graph, which is way too large. So that's a state explosion possibility. It's on the slides somewhere. I'm going to show it to you guys. Yes?
It's possible for TLA plus to run out of memory.
It's also possible in theory. But as I said, itself is actually quite efficient. So I think for the system that we're going to have you try in this course, it might just be fine. But in general, if you try to use TLA plus for some other much larger problem, it's definitely possible to run into state explosion. Yes, for sure. Okay. I'll try to see if I can give you guys some example to look at, but don't try. It's going to slow down your system. Right? I'll give you some example, maybe a little bit later. Okay, awesome. That's about lab number 1, part 2. Please take your time, digest the material, and let me know if you got any question. Okay, so today we're going to continue with the review quickly, which will be relevant to what we're going to see later. The first one. So we talk about universal existential quantification and with some simple example. The next topic will be how can we prove or disprove each of the quantification. Let's take a look. I have some example that I used to cover in 3342. Let's cover very quickly from scratch, just in case you got any further question. I also got slightly more challenging exercises for us to do. Okay, both. Let's do both. Let's go over the principle quickly. So on this page here, we're going to summarize about a proof strategy together. Okay. Number one, we got for all. Oh, how about this? This is how you can read it. For all, we can either try to prove it or disprove it. For exist, we can either try to prove it or disprove it. So we cover all the possibilities. Okay. Let's now try to go with this one. How are we supposed to prove that this universal quantification is actually true? Right? So there are more than one way. Patrick, you may want to say one.
And then do some logic.
And then show that PI is true. Absolutely. Okay? So it boils down into how can you make this implication true? And of course, if you review the lecture from previous classes, we talk about the truth table for implication, right? One way to make it true is approach number one. Assume R of I is true, and then you can prove P of I. That's one way. This means you have to somehow show that for all the possible I that satisfy R, they actually satisfy P. So this is considered a harder approach because somehow you have to consider every element in the collection or in the range so that they satisfy the property. So this is the harder approach. But if you got to do it, you got to do it. I would say harder. Is there another way in theory? Yes. Yes, exactly. Because we know that implication trivially will be true if this is already false. Remember the array example we talked about. If the array is already empty, universal quantification is automatically true, right? So number two, the strategy would be simply prove. Not the case, Ri. So this is analogous to empty array.
That's like the fantasy case. It's very true that the antecedent is false. Like generally speaking, it's not really representative of the majority of the
Yeah, it's one possible cases. But I think in some cases where we want to do proof, some cases you can argue that trivially, yes, but not in general. Absolutely. No, you only prove that somehow Ri is actually not the case. It's not possible to satisfy this. For example, let's say this. I'll give you one example. Ri could just be, let's say, defined as, let's say, I less than 0 and I larger than 10. Right? In this case, do you really have to go through all the integers? You don't have to, because somehow these two intervals are simply not overlapping at all. It's not possible to be in both range at the same time. So it'll be false. Just one example. So if I say this implies certain property on I, right? Let's say. In that way, you only have to show that, oh, this is not possible, right? I already got this one already false. So I don't even need to look at this one here. So this is already false. So the entire implication is true.
But don't you also have to prove for within that range?
Well, you can definitely argue. You're going to argue that there's no such integer that will actually satisfy both constraints at the same time.
Oh, okay.
Yeah, but you don't really have to explicitly go over every element. I think that's the point to note. Yeah. All right, so this one here will just be false, for sure. Good question. The second one, okay? The second one here, let's now go this one here. Let's say, how do we disprove universal quantification? P of I is false, okay? But what about Ri? Because if Ri is false, Pi is false. False implies false is true, right? So proving just Pi is false is not enough. You ought to really say that for there's got to be an I such that it will satisfy the range, but it doesn't satisfy this. That's what you got to do. You want to find a witness. Contradiction, exactly. And I'm going to give you guys some very interesting use of a model checker right away. Okay, let me write this down. Okay, this one, the strategy will be give a witness or in this case, counterexample. Counterexample such that you have Ri is actually true, but Pi is not true. Okay? That's the only way. And I want to give you guys some very interesting use of this property here. All right? The example itself, of course, it requires a lot of scaffolding to really build it up, the model checker. I'll try to give you just an intuitive idea. Even that is actually interesting. One thing we want to know, when the model checker is trying to check some invariant property, whenever the model checker can tell you that, no, your invariant property doesn't satisfy, it need to convince you by providing with you a witness. So this is really the idea about error trace that you see from part 2 of the tutorial, error trace. And I want to talk about this error trace a little bit to give you more interesting example. Very interesting. Okay, I'll give you one example right away. Do you guys know about the puzzle game called Sudoku? Okay, in case you don't know. Okay, Sudoku. I believe it's something like this, maybe 9 times 9, something like that. You got basically different square, okay? And somehow some number might be filled in, and etc. And there will be some number that's left blank. The idea would be to really fill out the number such that you got the sum on each row and the sum on each column will sum out to be the same. That's a Sudoku. Okay? Now, can you guys imagine, given a Sudoku game, how is it possible to use a model checker to find you a solution? That, guys, is okay. I want to give you guys 1 minute, even though you have no clue. Think a little bit, okay? It's very interesting how this can be used. I'll give you a little bit hints. Number one, we are given a game of Sudoku with a left blank for numbers, okay? And of course, usually we're going to spend sometimes hours for the very challenging one to really find all the numbers to fill out the blank. And somehow this property over here can give us a solution automatically, somehow. This might be a nice way to tweak your mind a little bit to think about. I'll give you guys 1 minute. It might be worth thinking about. Yeah, I'll just give everybody just exactly 1 minute. And I'll take your thoughts. One more hint. You may want to think about if I really want to make use of this to let the model checker help me. What should PI be? That's a good question here. So basically, I want to use a model checker in a way the model checker can give me a solution. And or the solution itself is an error trace. That sounds a bit weird, right? Error trace, you would think, usually it should be something that shows your system is buggy. In this case, we're using the error trace to show us a solution that we will suffer to find. All right, just one more moment, and then I'll give you some idea. All right, any thoughts? Go ahead. Ri and Pi, okay, you can think about Ri and Pi that's simply just general predicate. Anything that's a Boolean will be okay. Can be arbitrarily complicated. Any thoughts? Anything? Yes? Okay, sure, no problem. Go ahead.
Sorry?
Go ahead.
No, I'm sorry, can you repeat what the...
What the question is? Oh, okay. I thought you wanted to ask a question. Yeah, so, okay. The question was, okay, let's repeat the question again, and I'll tell you how to think of it intuitively. Given a game, like a Sudoku here, usually if you want to find a solution manually, you got to spend hours thinking about different combinations. There is a way to actually encode this in a model checker such that the model checker is not going to check to see, okay, every gaming scenario is valid. That's more like an invariant idea. Instead, by using this kind of property here, it's going to give you a valid solution to fill out the blanks. That's actually valid. How? Jora, you want to say something? That's a bit too low level, a little bit. That's okay, good. Yeah, I'll take two more, and then we should really, yeah, go ahead.
So what if, like, so the invariant is something that doesn't change. So what if you set the invariant to be like all the rows don't add up to a certain value?
You're getting close, yes, Patrick.
P of I and HB is the puzzle correct? Like just a Boolean predicate like that.
What do you mean is the puzzle correct?
Like,
Is it a valid solution?
yeah, like is the solution valid? And you can break
You're
that down into
getting there, but not exactly. Getting very close. Okay, let me tell you guys. Okay, so guys, I think for this one here, I can point out to you, completely optional. We're not going to do something this complicated for this course, but only if you are interested. The way to do this, at a high level, we're going to have some symbol like this, and satisfy. Don't worry, I'm going to talk about it when we start a model checking lecture. Some property phi. Okay, so this will be a model of your system, and this will be a property. Okay, and this will be some check to be done by the model checker. So here, what will be the model? Model will be conceptually more like a conjunction of, you want to have some encoding or formulation of the board. Maybe you want to use some data structure in the TLA plus, like an array of array. Okay, that can be more like a Boolean. You want to put things together like a structure. And also, the rules of the game itself can also be a predicate. Of course, it's very abstract, right? Both of these can be turned into predicates somehow. Okay, conjoin them together. This will be a model for this particular game. And then, what you do is as follows. You're going to say, the model I just put over here satisfies the following property, which is no solution. I'm telling the model checker, I want you to verify the following invariant property. Check all the ways to really fill out this puzzle here. And the invariant property should be none of them is valid. That's what a no solution really means. And the model checker is going to tell you, no, you're wrong. Here's one valid solution. Okay, and Patrick also mentioned a very good thing. Can this take forever? Depending on how large the board is and also how many combinations. But I think for an industrial strength model checker, they should be able to do it in a reasonable amount of time.
Is this not just essentially brute forcing all possible solutions? Because like it'll tell you that you're wrong, like why you're wrong, but it won't tell you the way to make it right.
No, it wouldn't tell you how to make it right.
So
Yeah.
you're going to have to pretty much generate another model that's
Oh no.
probably wrong.
No. This will tell. No, this.
Well, it'll tell you what you did wrong, but that doesn't mean it'll tell you how to get the right answer.
No, it will tell you. I tell you why. So yeah, you'll give it a trace exactly. So let me write down something, and I'll take more question here. So you can think about this one here. If the verification failed, that means it's going to give you an error trace. And this error trace over here, this error trace is going to be a way to lead to a state representing the solution. Right? So the state over here would be, maybe for this, it has been filled out with some number. This has been filled out with some number, and this one as well. And that one there is a negation of no solution, means there is a solution. Conceptually, that's why it will be done. I'll make some remark. I think Patrick got a very good concept. I'll address that. Yes? Oh, this one here. Oh, don't worry. That one there. For now, that's something I will definitely introduce a little bit later. So this one is like a satisfies. And this should be a contrast with something like this. Do you guys remember what this is? Like a sequence, right? Like a sequence we did back in 3342. But don't worry about this. I'll get there. It's defined as. Yeah. All right, guys, let me recap. Okay, as I said, this example here, to really get to the 100% complete detail, that'll be too much for this course. But I just want to give you an idea what interesting application. Okay, I'll just recap, and then I'll also answer what Patrick was just concerned about. Given a game with many placeholders about unknowns, what you can do is try to encode the board, the structure of the game. Another game will be PEG Solitaire. Solitaire. Okay. Do you know PEG Solitaire? Okay, you can look it up if you want. That's also another possibility. Anyway, to get the structure and the rules of the game, how the game should be played, combine them together to be the model. And then you tell the model checker the property I want to verify is there's no solution in any states. If there's really a solution, the model checker will give you like an error trace, which show to you this is how you can get to that particular state where no solution is false, which means that's the solution. That's a very interesting use of the property. And to really satisfy those who might be hungry about how this can be done, I will just include as a reference to you on the E-class, just in case you want to take a look. Okay. Anyway, so that's one thing to note. And if you really want to take away something here, just think about how this can be done. I mean, just how to interpret this. And of course, state explosion could be a very valid concern. I think for the very strong model checker, they may have some very nice abstraction mechanism for the model checking, so they might just be able to reduce the state space. But we don't need to know. Good. All right, back to reality here. All right. So we're done with this, and we're done with this. Okay. Now, how do we prove existent? They exist over here. This one should be the easy case, right? All we gotta do is find a witness, right? Such that this will be the case, and this will be the case. Okay. So this will be just one approach. Find a witness such that this will be the case, and this will be the case. Well, it sounds trivial. It's simply because we are having a conjunction here. The only way to make conjunction true is when both are true. This is definitely the easy case for existential. And what about the final one? How do we disprove existential quantification? Yeah, go ahead. Oh, yeah, go ahead. Yeah, something like that, for sure. Think about how can I make this conjunction false? Either I can make this false, or I can make this false, either way, right? Let's start with the first one. Either I can just show that R of I is not the case, right? This also corresponds to the empty array. Is there any positive number in the empty array? No, it's false, right? Empty array.
You have to show that for all I.
Yeah, well, pretty much like this guy here. But you can somehow, you don't have to explicitly talk about every member. You should be able to argue some property there.
But after mean all I.
Yeah. You want to show there's no such I. Yeah, Jorah.
So like when we're talking about this, we can just reason about it, just say like, for example, that example you gave there.
Yep.
You can just say, obviously, nothing that falls is exactly.
Yeah, that'll be reasonable. So yeah, let's say, take that one for example. This one here, all you gotta say would be reasonable. Let's say this. You might say these two intervals. Oh, how about this? There's gotta be some justification. There is no I. Satisfying two disjoint ranges at the same time. Along that line, I think that'll be acceptable for sure. At the same time. All right, good. All right, that's number one here. What about number two? Number two would be somehow this does exist, maybe some element over here. What you got to do is you want to say Ri and then not Pi. Basically, you want to say that for every I that actually satisfy the R, you want to show that all of them don't satisfy P. Right? In that case, you have no witness to really choose. Okay? I'll put it here. For all I satisfying R, they don't satisfy P. And this one here is the harder case for existential quantification. So if you compare this one over here and this one here, they're kind of similar, right? You somehow have to try to enumerate what's really happening in that range over there, and then why every member there will not satisfy P. Patrick.
Why do you have to show R and not P? Why can't you just show not P for the same reason
Yes.
as not R?
Because when you actually got PI, it might be way too general. Sometimes it might help your proof to say that there should be some context for I. Well, I'm only talking about not I in general, like all integer. I'm more talking about all the I that's in this particular range. It might just make your proof easier. It's a very good question, yes. Let me put it down. It's a very insightful question. You can think about the R of I here will give you some context. Gives some context about I such that Pi might be easier to be proved false. Be proved false. Of course, if you can just directly prove that Pi cannot be true, that's also fine. But usually this will help. Yeah. All right, guys, any question? That's a quick summary about the proof strategy. Of course, as soon as, whenever we use it, I'm going to remind you. Okay. Yes.
So in this example, we've kind of been discussing that R and P are related in the sense that R is kind of the range of the problem and P is some predicate applying to the range. But that's not always the case with Boolean expressions. Sometimes we just have two unrelated expressions.
Yeah, that's true. So yeah.
In those cases, like, it's slightly different to prove, right? Because we can't
Yes,
make the assumption
of course. So in general, of course, R and P may or may not be related. But you rather hope that the one you're given, they might relate it in a way, right? Of course, it's a different angle problem, really. So when you do the proof, anything can happen. Yeah.
That's why I was confused about why can we do just
Yes.
P?
Yeah, exactly. So I would say you will hope this one can help you prove this, disprove this easier. Absolutely. Very good. All right, so if you guys are okay, why don't we do some very quick, easy exercises, and we'll do the harder one, okay? Okay, the easier one would be over here. Okay, we got 1, 2, 3, 4, but you can predict that I'm gonna exercise all the strategy, for you. How about we start with the first one? This one here, do you think you can prove or disprove? Proof? Okay, proof. It seems like every element here is larger than 0, right? Okay, good. So you don't necessarily have to really enumerate all the values, but in this case you can. Okay, so one way to do it would be, I'll just do it here. So you can say this range over here, yes, give me a moment. You can think about this range over here, specify X should be a member from maybe 1 to 10, like an interval. Okay, from 1 to 10, right? It's an integer, but at the same time, it's actually between 1 and 10 inclusively. So 1 to 10. And you can say each is simply larger than 0. That'll be good enough. Because in some way, when you actually enumerate this one over here, you're already telling me you are enumerating all, right? It's a little bit hard to really give you a precise rule. But my point is, if you really want to prove this universal quantification, you need to somehow argue for every elements in the range such that they really satisfy this. Okay? A little bit more general mechanism could be if somehow this range, let's say this is R, right? This is P, right? Maybe the range is somehow is very big, but somehow you can partition then into different sub-ranges, maybe R1, maybe R2, R3, and R4. You may have to do some case analysis to say that, okay, this range over here can be considered in 4 cases, 1, 2, 3, 4. And for case number 1, it satisfies P. For case number 2, it satisfies P, and etc. Okay? It's a little bit more general strategy. Sometimes you may have to do some partition. Huh? Oh, let's not worry too much about it. Yeah, that's a bit tricky. Don't worry. All right, guys, the first one, okay? How about the second one here? How about this one? Prove or disprove? Yes. Oh, sorry? It is a valid statement, yes, it is valid. Value 1? Oh, you want to disprove it? Yeah, of course, yeah. You just want, yeah. Disprove. And counter example would just be 1. Absolutely. Because over here you can see 1 is in this range, but 1 larger than 1 is actually false. Right? Good. And to be more complete, I'll write it down here for you. This one here, you can think about 1, a member of integer, and also 1 less than equal to 1 less than equal to 10 implies 1 larger than 1. You can see I'm just plugging in the 1 here, and also 1 over here, right? What you get is this will be equivalent to true implies false. So this part is true, this part is false. So you just get false. Okay, that's a complete argument. Yes. Yeah, it's a very good question. The reason this convention here comes from Rodin, which is like a theorem prover in 3342. Basically, it's trying to just formulate the nature of the universal quantification. The nature about universal quantification is we only care about those elements that's in the range. If that's outside the range, we don't care. Okay. On the other hand, for existential quantification, the nature of that will be conjunction, because you need to be both in the range and also satisfy this for existence. That's a bit like it's more like a pattern in the Rodin to actually help you actually better to formulate these two quantification.
Like switch between the two. For the and, the left side is that's false.
You mean to switch what? Sorry.
Sorry. Like you can't just switch the.
Oh no, you did.
The implication of the exists.
You don't really do that. You can in that way. Okay, I see what you mean.
But like the and for the third one, you can't just switch it to an implied because then that would be a different thing. Right?
That would be a different, yeah. That would be, you could do it. Yeah, basically in that way, okay, I tell you what I really mean. That's a good question. I tell you what that will be equivalent to. That one will go a little bit complicated, but let's do it. I'll show you here. Okay, let's say this. Let's say x integer, and also 1 less than or equal to x less than or equal to 10. And also, you want to do implication, let's say. Sure, no problem. Okay, interesting. I tell you what, this can be somehow fit into the pattern. This is okay, because we're being completely general. After the existential quantification, you just got this. This will be just equivalent to there exists x. Okay? True, and this whole thing over here. So what does that really mean? That means, oh, by the way, we remember P and, oh, let me write it down here. Remember, true and P is equivalent to P, right? That's the identity of conjunction. So it is okay for me to say this equivalent to this. So we are saying that if you actually want to put implication, the way to interpret that would be the whole thing over here simply belongs to the property. And you just got range true. That means you got to consider all possible x without any restriction on the range. It will be as if. So it's still possible to convert that into this. But I think for Rodin, because it's supposed to be some verification tool, it doesn't want to go 100% general. So that's why it's saying that whenever you want to specify existential quantification, always remember to specify some range, even though it's true. But rarely it will be the case. Specify the range and also the properties separately. So for this special case you're talking about, it will be as if you want to say true. That means you want to consider all the possible values in the range. Okay? Hopefully that makes a little bit more sense. Right. Patrick.
So generally mathematically there's nothing restricting us from Rodin's statement.
Absolutely.
It's
Yep.
more just because in Rodin we will write it this way, that's why you're following that pattern?
Yep. Yes. Actually, for all the verification tool, you'll find that sometimes it may not be exactly corresponding to what you learned in pure math. You have to support certain pattern that's easier for the verification, indeed. And guys, not too surprisingly, we're going to see this very soon. You have certain axiom to convert between. Already here, you say for every x, p of x, right, is equivalent to, not the case, there exists x and not px. In this case, we are being very general. This can be, this can be any predicate over here, either including conjunction, implication, whatever. We're going to need this axiom to show you some equational style proof. We'll do that. And I'll just write it down for completeness as well. So these are the axioms. And also, there exists x and then px, very general, equivalent to not for every. Exactly. Not, p of x. All right, very good. Okay, we'll get to these two axioms in a moment. And there will be some nice exercise for you guys to do. This will be also relevant to later. Okay, so we are done with these two. How about we finish these two, and then we'll take a short break. Okay? Let's do. Okay, what about this one here? Proof or disprove? Proof? How do you prove an existential quantification? Give a witness. Jorah, give me a witness. Oh, are you sure? No, 1 is the bad one. Because 1 larger than 1 will be false. So, guys, a tricky question for you. I'll write it down anyway. So, let's say this. Okay, guys, I'll give you one possible written test question. Okay. Is the following statement correct? Let's say it's a true-false question. Okay, I'll modify the wording a little bit, but so you can read the whole question. To disprove this particular existential quantification, we can just give a witness x equals 1. Right? That's incorrect. Because even though, yes, you can disprove it, but the witness you use is actually not the one. It's a very good one. I'm glad you mentioned. All right? So, not correct. Not correct. Because the existential quantification should be disproved. Oh, sorry. What I'm talking about. To really prove, I beg your pardon, I might confuse some of you. This one here is actually to prove. Let me finish that and then I'll write it properly. We really want to prove this because this is indeed true overall. We can give some witness. But the one you give must make the whole conjunction true. But this one here is going to make it false. Okay? For those of you who just found confused for 1 second, sorry about that. Not correct because the existential quantification is true, but x equals 1 is not a valid witness. Because if you try this one here, y larger than 1 for this part here is equivalent to false. So it's not good. Okay, just on aside. Sorry, say it again.
We can only prove true statements, we can only disprove false statements. Like if you say disprove this, it wouldn't make sense because it's a
Oh, depends on the quantifier we're talking about.
Well, well, you can't, like if a statement is inherently true,
We can try it.
you cannot disprove it.
Of course.
Because and if a statement is inherently false, you cannot prove it.
That's correct. That's correct. Yeah, exactly. Yeah. Good. So that one I wouldn't need to rephrase. Okay, good. All right, guys. Back here. So, Jora, give me one more witness that's valid. 2. Awesome. I like it. Good. So, witness would be 2. Okay? So, we can prove it. Absolutely. All right. What about final guy here? Proof or disprove? And I'll pick you first. Yeah.
This is a bit of a tangent, actually. I was just going to say,
Oh, you want to say something else? Okay.
generally it seems like it's easier to prove existential and then disprove universal.
Not necessarily. Okay, that might be worth revisiting again. If you remember back in the previous page over here, right? We said that it would be harder case for existential if we try to disprove it. Somehow you want to argue that for every element in the range, the property is not satisfying.
Yeah, that's what I said. It seems like it's easy to prove existential and disprove universal. Because I have to try to witness to both for the other two options.
Yeah, also depends on which case you're talking about, right? If you talk about just this case, it's not too bad, right? But you're right, yeah. In this case, yes, to really disprove the existential is harder if you talk about this case over here. And for proving universal, it's also harder for this one here, but not this one. Okay, I kind of misunderstood what you meant. Yes. Yeah, no, it's good. It's absolutely good. Good, man. Good, let's now do final one. Proof or disprove? Oh, Jora, you raised your hand. Go ahead. Disprove, right? That's really missing, right? Now, how do we disprove? Yeah, somehow you want to somehow you want to imply that for all the numbers in this range, they cannot satisfy that, right? Yeah, that'll be one way. Absolutely. You can say, for example, the maximum value over here is 10. But 10 larger than 10 is actually false. So it's not possible for any value to be larger than 10. Very good. All right, that's the easier example here. Why don't we take a break, take attendance, we'll do the harder one after the break. Yes, I'll take question first before I take attendance.
I was trying to figure out, how did the machine prove this? Would they have to set so the intersection was set in the left and
Good question. I think depends on what tool you might use. Guys, just for your information. Normally, you wouldn't have this kind of like a theorem directly to be run by a model checker. Well, it depends on how large the range is. In theory, you can code it up, but this one may be something you want to use a theorem prover. Usually, they got many inference rule behind the scene, which can help you auto-proof. Yes. All right, good. All right, guys, why don't we take a quick attendance, and we'll let you take a break, and then we'll do a harder one. Slightly harder. All right, I think I already got it ready. Okay, 4315. Poe. And then our favorite question here. I still haven't got rid of F, but anyway, I'll try to if I remember. But who cares? Okay, good. Oh, actually, it's a different one, right? Oh, it doesn't matter. Okay, anyway, just choose an option there. All right, any problem you might run into, please come to me right away. As soon as it stabilizes, I'm going to stop. Okay? Any problem you guys run into? Everybody's okay? 35. All right, I'm gonna stop the poll. If you got any problem, please come forward. Otherwise, guys, take a 3 minutes break. Don't go too far, all right? Good. Proof by contradiction.
Quantification, right? Like you assume the antecedent is true, right? Like you're trying to disprove a
Yes.
quantification.
Yes.
Assume it's true, you end up with something false.
Yeah.
And you're using rules of inference, and then you
Somehow, yeah, but we wouldn't really use that a lot in this course. But maybe I can mention that maybe more completely. Yeah, sure. Go ahead. Oh, problem.
Yeah, I don't know if this matters. Like,
Okay.
I have 100% attendance, but I have 50% score. I don't know what that means.
Score might be fine. Might be fine. Okay. Andy, you got problem. Okay, sure.
I was going to ask you a question about the lab.
Okay, you know what? How about approach me after class? I remember your case. Good.
So for model M1, we have an invariance
Uh-huh.
where that's a plus b plus c equals to n.
Okay.
But because it's a refinement, this doesn't actually have a variable n.
That means you gotta declare that.
How do I declare that?
Oh, just declare a variable. It's like a
Oh, just
self-contained
declare
version.
it-
Exactly.
Just a self-contained. Okay.
Absolutely. Sana, question.
No, just the eye clicker thing didn't work for me.
Oh, okay.
Just keep saying
No problem. If you can, please find your name over here, and then, do you have a pen?
No, I can. I have one in my bag.
Yeah, grab a
Oh,
pen.
good.
Grab a pen. Yeah. Yep. Yeah, you can just find your name and then check mark and then sign. That'll be fine. It's sorted by
right
last
here.
name.
There.
There we go.
And then you want me to check here?
Yeah, please check here and then also sign.
Oh, okay.
Awesome. Thank you.
No worries.
Done.
I don't know why it didn't work.
Yeah, it kind of worked before, right?
I know.
Don't know. All right, guys, maybe another 2 minutes, and then we'll start with the more challenging exercise. Not too challenging, a little bit more challenging. Three and 1, 2. All right, guys, 1 minute, please. All right, 1 more minute. All right. Maybe not here. All right, let's resume. All right. I got 3 exercises for you. I'm going to turn into them very soon. So 2 of them are related to proving or disproving. We can practice that together. And for the third one, it's just about converting between quantifiers. That one should be rather straightforward. But anyway, we'll see. The first one. Okay. You got some quantification expression here. You want to choose all the statements that are correct. I'll give you guys some time.
In this course, how are we defining the natural numbers?
Oh.
Including 0?
Including 0,
Courses
yeah.
don't like that. Including 0 is good.
Maybe it was also Patrick. I think you also asked me a similar question in 3342. Yes, indeed. In this question, definitely, we include 0. All right, guys, just for your information. For this course, definitely, natural number is going to be 0, 1, all the way to plus infinity, conceptually. So definitely. We can definitely walk through the choice one by one. I just need the answer first. Not yet, not yet. Okay, take some time to think about. I'll give you guys who are struggling with a little bit hints. Basically, you want to think about this. Take a look at the pattern here. It's an implication, right? You want to think about the implication first. Is the implication true or false for every combination of x and y? That's what you want to think about. Natural number includes 0, of course. All right? Okay, any decision. You guys can chat, that's okay. You can collaborate in this context. You gotta be very careful about the choice because the wording is really important. Already, okay. Guys, first of all, do we agree if that's a theorem or not? Not a theorem. Okay, good. Not a theorem, first of all. So only 3, 4, or 5 potentially can be right, right? So now, is number 3 okay? Because 5 and 0 definitely are both natural number here. That'll be true. 5 times 0 will be 0, which is not larger than 0. That's a witness. I'll take a question. Give me a moment. Yes. So this one is definitely good. Over here, you can think about 5 is a natural number, and 0 is a natural number, and implies 5 multiplied by 0 larger than 0. And this part over here is definitely true. This part over here is definitely false. So true implies false. Overall, you got false. Not a theorem. So number 3 seems pretty good. All right? How about number 4? Is it? Well, this part here is right, isn't it? But what about the witness? Right? It's kind of related to the little mistake that Joel made before. Similar, right? So you can see, if I say I can disprove it using this counter example, but the problem is 12 times minus 2 is actually going to be minus number, right? That's not good. Let's see why.
That's not the reason, though. The reason is because negative 2 isn't a natural number. That's the reason why.
Yeah, exactly. Sorry, you're right. Let me write it down precisely. Okay? This part over here is correct. That's why I really need to write it down. But this part over here is inappropriate. Witness. Very good. But why is that? This witness over here is not actually going to make this implication true. Because, let's take a look. If I got 12, a member of natural number, and minus 2, a member of natural number, implies 12 multiplied minus 2 larger than 0. Right? You can see this part over here is definitely false according to our definition. False and anything will just give you false. And false implies anything will just give you true. Right? So it's not really showing that it's false. All right? So this will be just true. All right? So this is not good. And it's actually for a similar reason another similar reason. How about this one here? What about this one here?
Is appropriate, but the right-hand side is false while the left-hand side is true.
Mm-hmm. Yeah, Thomas, you want to say something? Mm-hmm. Actually, this number 5 is a bit tricky, right? But it's simply not right. Okay? Let's see why. Okay? It's weird. For instance, say, okay, let's say here. This one here, again, is correct. We know that. But this guy over here, I'll let you guys plug in the number over here. This one here, let me write it down very quickly. Right? That one there is going to be 12. It's a member of natural number. And also 13 is a natural number. And implies 12 multiplied by 13 larger than 0. Right? You guys can definitely evaluate this. This will be also just true. Right? You don't really choose a witness that evaluated true to show that it's not a theorem. That's inappropriate.
It's like general. It's true for this one, it's true for all.
Yeah, but it's more. We focus more about if you say it's not a theorem, you ought to show me a witness that will make it false. But you choose one that make it true. Right? Of course, this kind of question here, maybe in the written test, they are more likely to be a multiple choice. In which case, guys, just choose. You know. But in the exam, I might turn that into a written question, meaning that you got to justify. But hopefully, you guys feel more comfortable. All right, so the correct answer should be just number 3. All right. I'll take your question first, and I'll take hers. Yeah, go ahead. Yeah, go ahead. Yes, both of your written tests will be on E-class, multiple choice based mainly. In person, yes. William Small Center. Yeah, I think, when was it? I know, I remember, yes, Valentine's Day.
That's a written test.
Okay, Valentine's Day, you're right. Yeah, I remember one of the tests in my course is Valentine. Yeah, you guys are lucky one. I'll bring you guys chocolate. Maybe I should do that. Okay, we'll see. It's good, it's not a very big class, I can afford a chocolate for each. Anyway, go ahead, Sana. Small chocolate. Yeah, go ahead, yeah. Oh, you don't remember? Okay, I'm pretty sure it's not important. You'll remember later. Okay, good. You'll remember later. Okay. Yes. Oh, yeah, sorry, I forgot you.
I was just asking, could you repeat why it's not a theorem?
Sorry?
Could you just repeat why it's not?
Oh, okay. Because this is not a theorem because you cannot argue that all the combinations for x and y will simply just give to you that is actually larger than 0. Because when both are actually 0, right? In that case, for example, it's going to give you some false, so it cannot be universal. Right? Yeah. You first?
So if it's conditionally greater than 0, not strictly greater than 0, and then to argue this, don't we need some axioms?
Sorry, say it again. I don't quite catch it.
It's greater than or equal to 0,
Mhm.
then don't we need some axioms from number theory to argue this?
Good question.
It's about multiple.
Yep, I see what you mean. I think you will be okay, actually. So let me look. Yeah, I see what you mean. Give me one moment. Give me one moment. Okay, what you're talking about is, let's say this guy here is fixed change into larger than or equal to 0. Apparently, this will turn that into a theorem. This is definitely right. Right? Good. And this is basically what you can actually, well, there are different ways you can actually argue, right? So let's say x is going to be maybe from 0, 1, 2, all the way to plus infinity. And also y would be 0, 1, 2, all the way to plus infinity, right? You can say here, you can argue maybe 2 cases, actually. That's what you can do. But yeah, not really. You don't need that. You don't need that. Not there. Okay, let's say case 1. Case 1 over here, if in this case, if x larger than 0, and also y larger than 0, okay, then it's guaranteed x multiplied by y is larger than 0, right? And of course, x larger than 0 definitely satisfies larger than or equal to 0. Agree? First of all, that's case number 1. Okay, I have excluded this one here. This corresponds to, remember what I said before. Actually, I didn't know this can do. For an input space, you can partition into different ranges, different cases. Okay? So in this case, this one here definitely implies x multiplied by y larger than or equal to 0, corresponding to this. That's case number 1. What about case number 2? You can say x larger than or equal to 0, and also y larger than or equal to 0. Right? In that case, you basically going to say if it is possible for them to be 0. In that case, if one of them is 0, then of course the result will just be 0, which will still be acceptable by larger than or equal to 0. That's what you're going to argue. Yeah. Okay. Okay. So let's say if one or both is 0, that means x multiplied by y would just be 0. That means it is larger than or equal to 0. Yeah. Mm-hmm. Of course, if we really expect you to really justify, you guys write down what you think is the most detailed way to argue, and we'll judge. Okay. Yes?
I don't think we formally defined a theorem yet in this course. If you were to just give a one-sentence
About
definition of what a theorem is, maybe
what,
just...
also what an axiom is.
Yeah, like
Sure.
a theorem is just a statement that is always true.
No, it's contingent.
Yeah.
Okay, sure. No problem. So when we talk about axiom, it's basically an axiom. How about it? Let me put it this way. An axiom is assumed to be true. No need with no need for proofs. Okay, that one is good. A theorem is let's say, a Boolean expression, or like a predicate, right? A Boolean expression that requires a proof to show that it's always true. Okay? And we wouldn't really use it much, but you guys may have heard about lemma as well. Sometimes when you are trying to prove a theorem, you may want to break it down into maybe different cases and then prove in the intermediate lemmas. Okay? It's like a sub-theorem in some way to help. Okay. All right, good. Axiom and theorem. Axiom and theorem. Very good. Okay. And of course, in TLA Plus, you will be able to actually get axiom in the context and also the theorem, which is the property you want to check. Okay. Second one, guys. Okay. How about this one here? Apparently, the only difference is you can see exists, right? Now, what should be the choices that are actually correct? Mm-hmm. First of all, is it a theorem or not? Seems to be a theorem, right? As long as you can find a witness, in this case, for example, 3 and 4, right? Good. It's a theorem. So you can immediately not to consider any of these, right? So all you got to choose would be 1, 2, and 3. Okay? Okay, guys, please, please, please. Okay? You guys are getting excited. Very nice. Okay, number 1, should number 1 be okay? Yes. Okay, it is a theorem, we agree. And it can be proved by 5, 4, because 5 times 4 larger than 0. That's good. And they're natural number, exactly. Let me just write the first one down so you can see. So 5 is a natural number, and 4 is a natural number, and 5 times 4 larger than 0. For sure, it's true. Not a problem. What about number 2? Same, right? What about number 3? Why? Minus 2 times minus 3 is larger than 0. What's wrong? There's no implication. So guys, so why is that wrong? Here, minus 2 minus 3, minus 2 times minus 3 larger than 0. What's wrong? It's true. Yeah, the overall conjunction is false. Exactly. The range constraint over here is false. That's the problem. This might be a trickier one, right? I'll write it down. This one is no. Okay? Yes, well, that's another story. Okay. Not a valid witness. Because, let's try this. Minus 2, a natural number. And minus 3, a natural number. And minus 2 times minus 3, larger than 0. This part, I agree, is true. But the problem is the other part, false. And we're talking about conjunction. Okay, so this part over here is actually false. Overall, we still get false. Tricky, but still logical. So in your written test, of course, you guys got to be very, very careful about what's being said. All right? All right, good. Exercises, okay? And we got about 8 minutes. How about I show you one more thing, and we are done with the math review. We can start you fresh, model checking for sure. I already uploaded the slides about some more targeted introduction about model checking. I already put it up. In case you want to skim through, not required. If you want to, you can definitely go there and take a look if you want to. I'll show it to you. Yeah, model checking over here. And I think next time we'll do very quick, more targeted introduction about model checking, and then we'll talk about LTL, at least the syntax, okay? And let's finish the final part about the review, which is about conversion. And this will be some nice example for me to show to you some equational style proof. Okay, I'll show that to you. I think that should be just enough. And for the conversion, I think there are 2 things you guys can try, right? The second thing is about equational proof, which I'm going to show to you one example first. The first thing is, I'm not going to write it down. How do you interpret about the formula over here? When you try to convert from one into another, okay, you can basically substitute R and P by some predicate, some property, right? Let me try to see if that might help, okay, in case you're not convinced. So here we say that, let's say, for every X, and X is a student in 4315. If they are there, that means they receive an A+. Hopefully that will be true. I really hope. Anyway, that's not the point. Yeah, I'm more optimistic than you are, which is good, right? Okay, we'll see. Okay, sorry, I lost the point. Okay, here, so we're saying everyone in the 4315, that means they actually got A+. What does that mean? That means there is not a single student in 4315 who does not receive A+. Isn't that nice? That's how you interpret that. Okay, how about this one here? Okay, how do you interpret that? There is one student in 4315 who also received A+, at least one. That means it is not the case every student in 4315 who does not receive A+. If I say there's at least one, that means not all of you none of you actually receive A+. It's a little bit tricky to interpret. That will be some little exercise you can try to convince yourself. Okay, but now I want to show to you equational style of proof. This will be very valuable, especially for the final part of the course about program verification. Let me show to you. Okay, how do I prove this? For example, here, equivalence. Okay, what we're going to do is equational style. Equational style of proof. The structure is somehow very straightforward. You want to make sure every step you show in the proof, you put some justification. Okay, let me show to you. Okay, let me start with the first line. Let me copy just the first line, so that'll be our starting point. Okay, so it's going to be for every x, r, x implies p, x. Let's start with this. Okay, and do you guys remember the axiom I just mentioned before the break? Let me show to you. It's exactly over here, right? This is a very general form of the conversion. Any predicate I put for all over here, I can just put double negation over here by swapping the existential for all to exist. Okay. Now, don't worry, I'm going to mention it in the proof. So this is what you should write in equational style. We'll do lots of practice, don't worry, once we get to the program verification. But this will be the first one. What you're going to do is you're going to say this will be equivalent to, and here you have to give some reason. So here I can say the reason will be the axiom. For every x, px. You know, of course, I can try to use a different character just to avoid confusion, qx. This is equivalent to not there exist x, not qx. Okay, I'll let you guys digest this one here very quickly. So this is an axiom, which we said you don't need to prove. That's something taken for granted. And based on this axiom here, we can turn this left-hand side to the right-hand side over here, based on this. Okay, let's now do that. What I will do is I'm going to say not for every x. Of course, if I want, I can put parentheses if I want to. Let's say we put parentheses. And then, not the case, and you can think about this entire thing is like q. Think about this entire thing over here is like a qx, similar. And you're going to say not the case r x implies px. Okay, you want to really make sure you're convinced that this guy here is really corresponding to this guy over here. Because this one here is really corresponding to this one here. Okay? Yeah, think about it, after class as well. Okay? And now, how can we go further? We are getting very close to this guy here. You can see not there exist, not there exist. Somehow this part here is not exactly this. Jora, go ahead. Exactly, not P or Q by definition, right? Very good. That's something we did mention in the propositional logic. All right, so that's something we can definitely do. And equivalent to, and here we know that, let's say P implies Q is equivalent to not P or Q. Okay, for now, I'm just going to make this at the bottom here. Okay, and then what would this be? Not there exists x, not, okay, this part here need to be rewritten. Not Rx or Px, right? What else? Patrick. De Morgan plus double negation. But it's okay. But let's do one at a time.
I'll ask after.
Oh yeah, sure. Yeah, okay. Let's now do this. Let's say De Morgan. De Morgan. If you got not P or Q equivalent to not P and not Q, we're getting very, very close. This one here is going to be not there exists X, and then I'll say not Rx and not Px. We are basically moving from here towards over here, all by equivalence, equational style. Okay? Finally, just for this one here, double negation, right? Equivalent to, let's say, you don't necessarily have to mention the name, but I'm just trying to be very complete. Not P will be P. Okay? Almost there, just be complete. Rx and not Px. And take a look, starting from here, ending here, ending over here. Equational style. The essence of that is for every step over here in the middle, you gotta give some reasoning. Okay, maybe it's for some temporal logic property I can try to practice together with you guys again. Once we move to the second part of the course, maybe the last few weeks, we're gonna learn about Hort triple, the way to prove it in the equational style. But I think it's good to introduce to you guys earlier. Okay, thank you guys. I'm running out of time. We'll definitely start you fresh with model checking. See you on Thursday.